and react on the thermodynamic fluctuations of a system. So in our case, the qubit. And you can show that each bit of information can be converted or is equivalent to a negative entropy that you can then use for a thermodynamic process. So in our case, we are just heating and cooling the environment. So in the field of superconducting qubits, there's one thing we always get for free, which is decoherence. So there's we have macroscopic quantum objects, solid state quantum objects that get to the next slide. That's coupled to various loss mechanisms. So for instance, positional defects, we have dangling bonds, absorbed molecules on the surface, quasi-particles in the superconductor, and phonons, and so on. And by the end of the talk, I hope I can convince you that we have to add one more item to this list: lossless or long-lived two-level systems. Okay, let me briefly show you the device. So we are working on high impedance qubits, fluxonium qubits, that we implement with granular aluminum. So on the top, you can see the readout antenna. I have to show pointer. Okay, I can't. Do you see my mouse? Yeah.
Yes, we can.
Okay, so at the top you can see the readout antenna that is galvanically coupled to the superconductor loop of the fluxonium. And all parts in red here are made with a high kinetic inductance of granular aluminum. And we also implemented a squid junction to be able to tune the Josie energy over a wide range. That's now here shown in the right image. And with that, we were able to find a spot where we have excellent readout conditions, meaning that we have a fast and quantum non-demolishing readout. So that means when we measure the qubit, we want to find the qubit also in the state where we measured it. Okay, so when we measured T1, we found slight deviations from an exponential function. And this reminded us of an experiment that was done at MIT from Gustafsson. And here they showed that the sequence of pi pulses separated roughly by 1 T1 could increase the relaxation time of the qubit. And they argue that they were able to excite the quasi-particle or remove the quasi-particle background. And with our qubit, we were able to replicate these results, so shown here. So the pi pulses were like 100 microseconds apart, and we get qualitatively a very similar result. Quantitatively, our qubit is much longer, like 10 times longer lived. And the question was if you maybe could enhance this effect and maybe understand its origin. And here, the quantum Szilard engine comes into play. So this intelligent measurement apparatus here is now represented by Leo Szilard, its inventor. And we emulate this intelligent being by our measurement and control apparatus, operator X from quantum machines that orchestrates the whole experiment. So we measure the qubit via the dispersive shift of the readout cavity, readout antenna. So the measurement pulse reflects at the cavity, is then amplified by a homemade parametric amplifier, and then recorded. And in dependence on the measurement outcome, we can decide whether we have to play a pi pulse to bring the qubit back to its desired state. So the measurement is now depicted here, or shown here. So this is the complex reflection parameter. On the left, we have the qubit in the ground state. So our qubit is at 1 gigahertz, so it's thermally populated by 12%. And after the active reset, we can bring the qubit to the excited state. And we achieve this with a readout pulse length of only 128 nanoseconds, and we get a state separation of 5.6 sigma. So now the idea of the experiment is now as follows. So in the beginning, we have a stabilization sequence where we measure the qubit and bring the qubit always to its target state. For instance, when we want to bring to stabilize the qubit in the excited state, when we find the qubit in the ground state, we play a pi pulse. When we find it in the excited state, we do nothing. So we repeat this for several times, capital N times. And after the stabilization, we initialize the qubit, again, either in the ground state or the excited state. And then we monitor the qubit relaxation by recording stroboscopic quantum jumps. And such a typical quantum jump trace is shown here. So the qubit started here or was initialized in the excited state, and after some time, it decayed to the ground state. And eventually it gets re-excited due to the finer temperature of the environment. Okay, so now if we average a few thousand these traces together, we get the qubit relaxation. So here on the left, we have the qubit, on the y-axis, we have the qubit population, and on the x-axis, the time. And note that for reasons that will become apparent in a moment, we plot in log scale from 300 microseconds onwards. So this is now for n equals 1. So if we increase the stabilization, we see that the relaxation changes and gets slower and slower. And for n equals 10,000, it's so slow that after 10 milliseconds, there's still a population left in the qubit. So the question is this really T1? And there's a simple experiment to prove it, which is to initialize the qubit in the ground state. And if the qubit, so if this is T1 is real, the qubits should stay in the ground state and slowly warm up back to thermal equilibrium. So instead, what we see is that the qubit rapidly heats up, which is of course very disappointing in the beginning. But then we soon realized that the qubit overshoots 50%, so reaches population inversion. And that made us very excited as well. So let's maybe briefly check that this is not an artifact. So here after 100 microseconds, we can clearly see here on the right plot that we measure the qubit more often here at the top in the excited state. Okay, so with this quantum jump traces, there's one important thing we can calculate, which is the transition rates, which we can extract from the probabilities of successive measurements. And these probabilities can then convert it to the transition rates of the qubit. So gamma up and gamma down, which are now plotted here for different stabilization times. And for a well-behaved qubit, these rates should just be constant. Instead, what we see is that these rates are like bending here in the beginning, and actually for long stabilization, they are inverted. So the qubit really sees a negative temperature environment. So the qubit wants to go to the excited state. Interestingly, we can also compute these rates now when we flip the qubit in the end to the ground state. And here, the rates change. So they are the red curves and the green curves. They are a bit more back to the original value. So that means we are cooling with this one pulse the environment. And that tells us that the environment is of finite size. So it stores only a few energy quanta. Now, if we add these rates together, we get the relaxation time. And the relaxation time, here in violet, is comparably constant, or is constant. And I added here already the theoretical lines on top for better, for more clear view on the data. Yeah, so the constant relaxation time, as well as the population inversion that pinpoints to a two-level system environment. And this brings me now to the theory. So we assume that these TLSs are spaced in frequency, probably randomly spaced in frequency, but for the modeling, we assume that they are like equally spaced in frequency. Now the cross-relaxation rate is given by this Lorentzian function here in the detuning, delta k. And these rates, we plug them into a rate equation that we can solve numerically. And it also incorporates intrinsic relaxation rates gamma q and gamma t. So gamma q for the qubit and gamma t for the TLSs. And with this rate equation, we can fit the measured data. So here for one curve up to 1 millisecond. And if we include now the heating process to the modeling, we can describe all the measured curves simultaneously. Now, might be still the question if this effect is, so if this is really related to the Szilard engine. So is it really the information of the qubit state that is used to heat the environment? Or could the CT be maybe the result of a trivial pumping, like we have it in a laser, pumping higher levels and so on? And again, there's a control experiment that we can do, which is to stabilize the qubit in the ground state. So when we keep the qubit in the ground state, we should extract the energy from the environment, and we should find it in a colder state. And this is indeed possible. So here, when the qubit starts in the ground state, it stays longer in the ground state and then slowly warms up. And also if you start from the excited, so initializing the excited state, qubit rapidly cools down, overshoots here at 1 millisecond, and then slowly warms up. And the solid lines here are plotted with the same parameter as in the previous plot. What we can also describe now is the experiment I showed you in the beginning, the experiment from Gustafsson. So here on the left, we have the relaxation for different number of pi pulses. And an experiment that they couldn't do back then in 2016 was this active reset. Now, if you actively reset the qubit to the ground state, what we see in our qubit is that the qubit again heats up. And also here, like for n equals 50, it overshoots and then slowly cools down again. So with these pi pulses, we are also just heating up the environment. And again, we are not improving the T1 time. T1 is constant. Okay, so what can we learn now from the model? So first of all, we can only fit this data if these TLSs are extremely long-lived, longer than 50 milliseconds. Second, these TLSs provide the main relaxation mechanism. So in the absence of these TLSs, we would have a lifetime of 90 microseconds instead of 20 microseconds. And if we assume that the qubit provides the main decoherence mechanism, we can extract a coupling strength of 12 kilohertz, and we get a TLS roughly every 150 kilohertz. So they're extremely weakly coupled, and a lot of them. And yeah, this brings me to the end already. So I showed you that this Szilard engineer can uncover hidden environments, and these long-lived TLSs provide the main loss mechanism for our qubit. And finally, one point that I want maybe as a take-home message: the relaxation time T1 is independent on the TLS populations. So I read about many proposals where you say that they say that saturating the TLSs could improve the qubit coherence or qubit lifetime, and this simply doesn't work. This might work for resonators, but not for a qubit. So T1 is independent on the TLS populations. And with that, thank you for inviting me, And yeah.
Thanks for your presentation. And now if anybody has any questions, you can write them in the chat, or you can just ask them directly, please. So while people decide whether they have questions or not, let me just say that with every presenter, we ask a few questions. There was a question that we always ask. It says, can you enumerate your top 3 dream employers, companies that you'd very much like to work for or intern with, or any other plans that you have for the future? And so Martin's answer here was, in Germany, quantum computing companies are still in the early stages, which is why I'm planning to continue as a postdoc, which gives me the opportunity to mention something that Jonathan Felbinger, our deputy director, mentioned a few days ago. He said that in the past 12 months, QED-C has grown, has expanded internationally, and now includes companies headquartered in 37 countries. So anybody, any questions for Martin?
And maybe I can ask a short question, Martin.
Mm-hmm.
So the Fluxonium qubit is obviously, it's a fairly long-lived superconducting qubit. And I know that your team is working on this traditionally. Did you pick the qubit type because of the study that you want to do, or the TLSs, or was it the other way around, that you found the TLSs and you figured that this is a good platform?
Yeah, the other way around. So we're interested in this material, and then we discovered these TLSs. But I have to say, I'm not sure if there might actually exist also in other Fluxonium qubits. So I've seen similar experiments, like one from Gustafsson was a flux qubit that also showed these long relaxation times. So I'm not sure if granular aluminum is the reason for this behavior. But yeah, so if you want to build really long-lived Fluxonium qubits, I would probably not go for granular aluminum. There's a lot of stuff going on. So
yeah, it could be a good platform for material studies.
Yeah, and it's the high kinetic inductance is definitely interesting for example, Purcell filters or other objects that you need in a superconducting hardware.
Yeah, thanks.
Okay, so in the interest of time, if anybody has any other questions, please mention them. Otherwise, I'm going to move into the second presenter, if that's okay. And thank you very much, Martin, once again for coming today. Philip Krantz. Yes, thank you once again. Philip Krantz is a business developer and quantum physicist in the quantum engineering solutions team at Keysight Technologies. He's working to expand the customer base of the quantum measurement software that they develop, as well as providing hands-on expertise in quantum engineering. He is also lead for customer and industry partnerships. Before his appointment at Keysight, he had received his PhD in experimental quantum physics at Chalmers University in Sweden. He also spent 3 years as a postdoc in the Engineering Quantum Systems group at MIT, as well as 2 years as the scientific coordinator of the Wallenberg Center for Quantum Technologies in Sweden. His presentation today will show how to build a quantum demonstrator based on a nitrogen vacancy center qubit. The aim is to provide a cheap yet powerful quantum system aimed at educational demonstrations where there is no need for neither a dilution refrigerator nor an optical table. Quantum system itself is the size of a Rubik's Cube, he says, and he will show us how to control this device using Keysight quantum control electronics. Philip, take it away. So he's going to share the screen now. Somehow can you hear me? And can you share the screen, Philip?
Hello, everyone.
Hi, how are you?
Sorry, my internet connection crashed when I was trying to share screen. So let me try again. There. Can Wonderful. You see my screen now?
Beautiful.
Great. Thank you for the introduction, and thank you for inviting me. I'm actually stepping in a little bit here for one of our interns, Asin, who completed this project during her internship at Keysight. So I'm here today just to tell everyone about her work. yeah, the main idea here is really to build a quantum demonstrator. So to be able to find a system that you can use in educational purposes and to be able to demonstrate quantum phenomena in an easy way. So that's what I will talk about today. And the system is based on NV centers in diamonds. And yeah, so what's the motivation for doing this? I think it's obvious to the audience here why we want to do this. And as you all know, that there's a very big push today in terms of the workforce in quantum, and to be able to find new ways to educate this workforce is becoming more and more important in particular for universities. But the problem with these systems is that they are usually fairly large and expensive. And as you know from Martin's talk now, working on superconducting qubits, it requires a lot of infrastructure. And even if you do have access to this infrastructure, it is not always students have access to the infrastructure. So the same goes for optical systems, that if you look in a lab, it's typical fairly large setups that you find. And as a student, it could be quite intimidating to enter a lab where you don't understand anything, and there's just a lot of overwhelming equipment there. So what we wanted to do is to find and explore what can we use in order to educate people about quantum without having an excess of equipment. So that was the motivation from our side. And the system that we picked is NV centers, for the reason that they can be operated at room temperature. So we don't need any cryogenics. And we can also operate these with control and readout pulses in a fairly easy way without having a large setup. So this is the setup that we have for demonstrating a quantum system. And in addition to the electronics here, you have a small device about the size of the Rubik's Cube that Adrian mentioned, is the actual quantum device. So this is all you need to demonstrate a quantum phenomena. And the idea then is that this is an off-the-shelf platform that is ready to use. And it includes everything that you need in terms of control and readout. And as you can see here, the motivation from Keysight side is that we supply the electronics to control this device. And it's built around the PXI system. The way this works is around the Labber instrument control software. And we use Labber to orchestrate the measurement, connecting it to the different instruments that you have. So you have AWG, SMU, digitizer, and a vector signal generator here. Out of these instruments, I can mention that the signal generator is a bit overkill for this application. It's a fairly expensive and big instrument. You don't need this sophisticated signal generator for this. And what we do then is that we connect this to the device, which comes from a startup company, SB Quantum, in Canada. And I should mention also that this is a collaboration between Keysight, SB Quantum, and the Sherbrooke University Institute Quantic. And as you can see, this small box here contains the diamond, and it has a nice interface that you can connect the electronics to. So the setup looks like this. You have a PXI chassis here, and with an embedded controller. So the computer sits inside of the PXI chassis. You have an arbitrary waveform generator to control the laser inside of this small Rubik's Cube of a quantum system. Then you have an AWG also to control the mixer inside of the net or the vector signal generator, as well as an SMU to control the laser also in here. And as you can see also, this is called a SB quantum magnetometer. So the device itself is actually a quantum sensor that is used to detect magnetic fields in a very sensitive way. So that is the main origin of the device and why it was built from the beginning. So the Labber framework, I don't know if you're familiar with Labber, but it's the instrument control software where you have an instrument server connecting to all the instruments. You have a measurement editor in which you perform the measurement. So this is also something that's very easy accessible for students. as well as a log browser to keep track of the data that you record. We also have a Python API, so everything here can be done programmatically through Python, which is also something that is important for students to learn. So next, the results that we can get, so some typical data out of the device would typically start with doing spectroscopy or looking at the characteristic behavior of the device with ODMR. And this means that we want to find a bias point essentially for the continuation of the experiment. So after doing this, we can zoom in on one of these triplets of peaks, and we can find the center frequency by fitting this trace, and then we can perform a Rabi measurement on the data. Obviously, this is not as long-lived as smartest fluxonium qubits, but nevertheless, you can find Rabi oscillations, and it behaves as a quantum system. So this is just a starting point of experiments. You can continue and do all the typical quantum experiments using this very simple device. And it's surprisingly how easy it is to operate and how fast it is to get to this point, which is another point for students that it's quite easy to be scared away with very long experiments to get to the actual quantum behavior. And by then, they might have left the lab already, going for another career. So I think it's very important for the quantum workforce to understand the core foundation of a quantum system. And this platform allows you to do that. So the summary here is, I think we can summarize with this image here, that it's a very simple off-the-shelf system that you can do quantum experiments very easily with. And having access to very easy and small electronics to go with this is also something that's ideal for student labs. And finally, and that maybe most importantly, it's a cost and space efficient solution for doing quantum experiments. So that's another aspect that is important for many labs. If you want to know more about this or just reach out to us, you can also find more information on our website at Keysight. And our core activities is around these quantum control systems. So that's what we're designing and providing to customers. So that's my last slide. So thank you very much for listening, and let me know if you have any questions.
Right. So questions for Philip.
Okay. So Philip, I have a question. This is Chris Bishop. Thank you for sharing this. Can you give us a sense of who's using it? I think it's great that you're offering, a cost-effective solution for this kind of, investigation. Can you give us a sense of how it's being used?
Of course. Thanks, Christopher, for the question. This is actually very early in the development of this. So we just finished this internship with Asin. So what we will do now is actually to roll this out to some initial users. So the short answer is that there are no users out there yet, but that's what we're aiming to change. The target audience for your question is typically university labs where you have courses on quantum measurements. It could also be advanced electronics or even just electronics classes where you have some influence on quantum. So that's our thoughts right now.
Yeah, great. No, thank you very much.
So you're in a stage of outreach right now, advertising and outreach.
Yeah, building some awareness and also I think in general just emphasizing the need of educational tools like this, maybe to inspire you to make another demo set for quantum experiments. So it's not only for building awareness around this particular solution, but more recognizing the need for training the workforce of quantum for tomorrow.
Wonderful.
Yeah, thank you.
Cecilia?
I'm curious what the rough cost is.
It's something we're actually working on. That's where we're trying to push down the cost as much as we can. So we are right now in the process of stripping down all the electronics to its bare minimum to see how cheap can we make this. I don't have a number, unfortunately, to give you today, but I can certainly get back to you.
Just
I mean, even a sort of target or, goal. I mean, are you trying to get it below 100K, below 50K?
Below 100K for sure. But we can see how far down we can push it. Our target here is really to reach as many people as possible, not to put an expensive price tag on this.
Yeah.
That's not the goal.
And just to follow up on this, if somebody had the money and everybody would agree on everything, how long would it take for you to deliver it?
So the delivery of this is actually a bit, the bottleneck is the SP Quantum startup company, how fast they can manufacture these Rubik's Cube. So the electronics is all commercial. It's something that we can provide from Keysight. So it's a question for someone else than myself.
Okay. Any other questions?
Yeah, Josie?
And yeah, this duplicates a question I put in the chat. So feel free to ignore that. I guess I'm just curious, have you done any work on how and obviously if it's very early prototype, this is probably not the case, but into how students actually or intended users actually interact with this apparatus? It seems really cool that we have this interface, but has there been any work on given this interface, what students do with it, how they reason about the quantum device under the qubits underlying it, what's going, has that been studied at all, or is that something you all are interested in?
So our target is to provide as good of an explanation and like a demo kit as possible, so that we can introduce the technology a little bit. We have not yet tested this on the target audience of beginning students. We tested it on the internship. Intern Asin, but she is herself in the PhD, in a quantum PhD, so she's not really representative of our target audience. But that's an excellent question, actually, and we will think about that, and we should create some
if that's
user
something
group.
you're interested in, I posted more information in the chat, but I have colleagues who are working on almost exactly the same questions, only for single photon experiments, if you're interested in connecting with them.
Very, very much so. Thank you. Yeah, I will definitely follow up on that.
Martin has a question.
Oh, sorry. Was there a link to pop in the chat for the Keysight Technologies? I guess it was. Sorry.
Yes, Martin.
Yeah. Okay. Yeah, I'm just curious which experiments you can perform. It's just single qubit experiments, or can you maybe also interact with the nuclear spins? Or?
This design of an experiment would be around a single qubit. So you can do all the different pulse schemes that you can apply on a single qubit. You can do quite a lot with that, but as soon as you start, you cannot do 2-qubit gates or anything like that. So I think that's the limitation. But given the target audience, it could be that it's enough with a single qubit. Yeah, but that's also something we have started to think about. What should the scope be? Okay, thank you very much for the questions.
Yeah, thank you once again. And so now this would give us an opportunity to move on to the third presentation. Josephine Maya. Josie is a research assistant and NSF graduate fellow with the Physics Education Research Group at the University of Colorado in Boulder. She began her physics PhD studies in experimental quantum metrology, but transitioned to quantum education research when she realized that her greatest joy was in helping others experience the excitement of quantum mechanics and quantum technology. She is particularly passionate about issues of ethics, culture, and inclusion in physics and quantum science, which she explores in depth in her blog, Beauty in Decoherence. And I'm going to put a link to the blog in the chat. Go right ahead, Josie.
Confirmation, can people see and hear me?
Yes.
Wonderful. So yeah, as was just mentioned, my name is Josie Meyer. I'm a graduate student at the University of Colorado Boulder, specifically studying issues of effective and socially responsible quantum education, which, as we see, connects with a lot of the workforce development and whatnot that QED-C is working on. So I probably don't need to spend too long on this for you all, but why should we be caring about quantum education? And particularly, why should we be caring about this now? Well, obviously, there's the workforce development aspect of this, which is if we want students to have the right skills to build this workforce that we're working to develop, we want to make sure that quantum education is effective. We're throwing a lot of money into, for instance, teaching or creating quantum computing courses and quantum information science degrees. Let's make sure that we're actually doing what they hope they do, and they're doing so as effectively as possible. This is also, I would argue, is an equity and inclusion issue. If we want to make sure that our quantum workforce is diverse and avoids a lot of the issues in the past that its progenitor fields like physics and computer science have struggled with, this is definitely an opportunity to affirmatively consider these issues in our work from the beginning, as we're still developing this infrastructure, so that we don't fall into entrenched patterns. And finally, it's a cool opportunity to shape the culture and direction of our field, because not only do educational initiatives at the beginning help provide the workforce, we can also use this to even shape how the workforce is thinking and the sort of research questions that might be asked, so that we can help build a workforce that isn't just capable of doing what we maybe are hoping for right this moment, but exceeding our wildest expectations. So I'm just going to talk about a handful of different initiatives we've been working on with our group, though there are many others. But I'm first going to start out with some broad work we've been doing mapping the landscape of quantum education in the US. Then I'm going to be focusing more on some specific projects like studying student reasoning in the context of quantum information science courses, incorporating ethics education in the quantum information classroom, and I'll give a little bit of an explanation of what that means. And finally, a new project we're working on that's like a scalable assessment to measure student learning in these courses and why this is valuable. So first, zooming out, landscape of quantum education in the US. So this paper is from one of my collaborators, Bianca Cervantes, asking, is quantum information science coursework equitably distributed across US colleges and universities? And sadly, the answer is not really. We've found, based on an inventory we did in 2019 to 2020, that these courses are disproportionately situated at private PhD granting institutions, and that and are less likely to be found at minority serving institutions, particularly underrepresented minority serving institutions such as Hispanic serving institutions and historically Black colleges and universities. Obviously, the number of courses has blown up since then. I've actually went and recompiled this list. We're doing some analysis as we speak. So hopefully some updates to see if this has changed at all. Sadly, it doesn't look like it has, and may have actually gotten worse. But this is, but we're doing this, and this definitely talks about the importance of reaching out to basically institutions other than the private R1 universities that are dominating quantum research as we speak. So next, we had a survey, again, back in 2021 to 2022, asking, what do instructors have to say about quantum information science education? And a whole bunch of interesting takeaways came from this initiative. We found, unsurprisingly, as many of you can probably guess, that this quantum information science coursework is offered across a broad range of departments, academic levels, like undergraduate to graduate. We did not specifically look at high school, though there are colleagues of ours who are doing so. Prerequisites and even instructor backgrounds. A lot of the instructors that are teaching this material are not quantum information experts or researchers themselves. Very often it's some random computer scientist or physicist that got roped into this. So there's actually a pretty desperate need out here for making sure that there are resources accessible to this population who's actually going to be teaching our future workforce. We also found that there's a variety of goals for this instruction, and there seems to be relatively little consensus on why we are teaching this beyond broad ideas like workforce development. Is are we teaching quantum computing, for instance, to undergrads because we want them to be able to run quantum algorithms, or are we more interested in using this as a backdoor to get non-physicists interested in quantum mechanics? I can't tell you which is the right or the wrong answer, but I can tell you that these are all themes that we heard. We also heard, somewhat unsurprisingly, probably for many of us, that students struggle a lot with the mathematics coming into quantum information science courses at all levels, especially linear algebra, where a lot of undergraduate linear algebra courses at institutions are just not covering the right subtopics of linear algebra to be giving the students the well-rounded skills that they need, like tensor products for even simple, for instance, quantum algorithms. And finally, this could be a call to action to anyone here who feels like jumping on this, but there seems to be pretty widespread dissatisfaction with available textbooks, particularly at the undergraduate level, where most of the books that are available are either outdated or beyond the undergraduate level. So if anyone wants to jump in on this, there is high demand for it, especially if it can be based on research-based methodologies of how to write an effective textbook. So I'll leave that challenge to you all. And finally, we have a paper under review looking at specifically a theme we didn't really ask about, but kept coming up, which was that quantum hype itself affects how instructional practices have to take place. And this can be good or bad. It's often bringing students in, but it's also creating a whole list of naive conceptions based on media coverage that are not rooted in science. And so it's interesting looking at how instructors basically deal with the fact that students are coming in thinking they are knowledgeable about this because they've read the popular media. And sometimes what they've read from the popular media is accurate, and sometimes it's downright garbage. And so trying to separate that out. So zooming in a bit, I think I'd also like to discuss some work we're doing studying student reasoning in the context of these courses. And I guess the question is, why study student reasoning? And the simple answer to it is that very often students don't reason the same way that experts do. We're trying to help build those skills, but we also want to know where students are at. And if we just naively use our own expert perspectives on how students reason about these, we can easily fall into a pitfall where our own understanding doesn't map what's actually going on in students' minds, and therefore we're building educational materials based on what we think might be useful rather than meeting students where they're actually at and helping them build the skills that we hope that they will. So a couple interesting studies that have come out of this. One being looking at superposition states. Pretty simple problem we like throwing at students because it gets at something that isn't necessarily really taught, but that I think we all can hope for, particularly at undergraduate level classes where students aren't really being exposed to the idea of mixed states. Give them two registers of qubits, one of which I initialize them all in a uniform superposition state. And another register where I basically use a random number generator to initialize them as either zeros or ones with equal probability. And obviously these are different, but an interesting question to ask students is, are these different? And then if so, how would you go about distinguishing them on a quantum computer? And students very often, especially at the undergraduate level, struggle with this. But what we found more interestingly is that once the challenge is not that students, a lot of students will be like, these feel different, but don't necessarily know what to do. And they know their quantum gates. If they've come through a undergraduate quantum computing course, they've applied Hadamard gates in every single one of their homework assignments, basically, and all the algorithms they've seen. And that's all you need to distinguish these, is to apply Hadamard and then measure in the standard basis. But students struggle to see that that's something that goes on in a quantum computer. It's not really a tool that can be used to reason about quantum states. So our challenge as educators can often be that quantum gates are a tool that the whole quantum workforce uses, not just for constructing algorithms, but for conceptualizing what quantum states actually are. And that we can model this as reminding students to, we talk about resource activation in education research a lot, which is students might have knowledge, but not bring it to the forefront of their minds, and helping and that's very important for ideas like gates, that students may know, but not necessarily be able to apply to unfamiliar problems. Another interesting thing we've explored is asking students after a quantum computing course to just explain like what makes quantum computers quantum. In other words, what makes this superconducting qubit quantum computer on the left different from just like some big summit supercomputer, classical supercomputer. And turns out students really struggle with this, which is kind of sad after they've just taken a course on this. But what we found is a really helpful intermediate bridge is to actually introduce the idea of an analog classical computer as a thought experiment. And this helps students really get past the superficial difference of calling, often in their own words, classical computers digital and quantum computers analog, in that the states have continually variable coefficients, which is true, but if that was the only difference between a classical and a quantum computer, we could just use vacuum tubes to make a analog classical computer that could do significantly more than the digital classical computers we can do today. Obviously, that's not the case. But by asking students to particularly compare and contrast what the analog classical computer can do versus the digital classical computer and versus the quantum computer, it really helps tease out the aspects like entanglement that are truly quantum about the quantum computer and where quantum advantage comes from, rather than focusing on some superficial differences like the analog digital distinction that so many students will tend to bring up. Finally, just some smaller projects we've been working on, but one is looking at incorporating ethics education in the quantum information science classroom. And so why do this? And I would argue it's because research takes place in the context of society. All of us that are engaged in this work have to deal with questions around like ethical use of defense funding, equity and inclusion, media hype, cybersecurity, and there's not really any right or wrong answers to any of these questions. But the wrong answer very often is to stick our head in the sand and pretend they don't exist. And so, quantum technologies have the possibility for widespread societal benefit. They also have the possibility for serious harm if, for instance, we create a quantum computing arms race that results in decrypting internet security. Or if this technology was to get concentrated in the hands of bad actors. So really by bringing these issues up, we can help make sure that researchers are informed to be talking to policymakers and to be thinking through what they're doing, so that however you decide to deal with this, we're doing so intentionally. And that we're deploying this technology thoughtfully, wisely, equitably, and in ways that, for instance, don't distort the market. And finally, some final work we've just started is working on a scalable assessment to measure student learning in quantum information science courses. So what do I mean by a scalable assessment? Well, this is not your final exam. In fact, one thing that we show all over and over and over again in physics education research and other discipline-based education research is that grades and exam scores, though they can be helpful for distinguishing one student from another in the same class, they can be misleading in a couple of ways. Students can ace exams because they've gotten really good at guessing the way problems are solved, but struggle to be taking basic concepts or struggle with basic concepts that experts take for granted. And also, it's very difficult to compare across courses. So what we want is some sort of diagnostic tool that we can use to compare learning across courses and across institutions to really identify what best practices, what's working, so that we don't have to keep reinventing the wheel. So how this works is we do the hard work of basically giving you as an instructor, a short, easily scoreable, ungraded pre or post test that you can give to your class. It'll be multiple choice or similar things, very often computerized, where all the stats are done for you. It has to be ungraded, otherwise it becomes an incentive to study for it, which obscures a lot of the information that we're likely most interested in. Is the class effective? And then we do the hard statistical work, which takes actually, in many cases, a period of years to design and validate the instrument so that we can give you feedback that based on a lot of psychometrics research and other work that has been ongoing for decades on exactly how this should be interpreted. So that, like, for instance, if you're finding that your course students are struggling on question 7, we have some sense of what that means. And when doing this, you can compare across course iterations or over time or across institutions. And this is particularly valuable if, say, you teach the same course multiple times and you want to test if like some changes you've made have actually improved student learning. Maybe they've improved how students respond to faculty course evaluations, but that just means that they maybe enjoyed the class more. It doesn't necessarily mean that they're actually learning what we hope them to learn. So this is a tool that can be really useful for instructors in helping us make sure that our teaching is as effective as we can. And so we are currently working on the early stages of this. We will be looking for institutions to pilot this probably in about a year or so. And we're also looking for some feedback on the instrument itself. So if this is something that it interests you, I do have, please feel free to reach out to me. I can put my email in the chat. And finally, I just want to throw up a couple of options coming forward before we ask for questions. I have this big QR code in the center, links to my personal site. It has my blog on it. It also has work we're doing, papers or various papers on this topic if you want to delve into any more of the topics that I've kind of given a brief overview on or follow things in the future. A lot of this is very relevant to educators in particular. If you're like, I want some immediate things I can apply to my classroom to teach more effectively. And this is constantly being updated. Also, if you're an instructor or if you know instructors that are teaching quantum information science, quantum computing courses, or have done so, I encourage you to send them this link on the right. I also have a QR code for it if you happen to be one of these people in the audience. We currently, for the month of October, have a survey, a brief survey. It's 10 to 15 minutes, honestly, probably takes less, on quantum information science education, where we're trying to figure out what the core content areas are so that we can focus our work on things that instructors will actually use. And this will inform some future curriculum development initiatives and assessment development initiatives. We currently have 95 responses as of this morning. We're trying to get to triple digits. This will be far and away the biggest survey of this that's ever been taken. With you all's help, we can easily get there. And if you're an instructor, basically what you're doing is saying, you know, we want to hear from you because we're basically asking you how we can best serve you. Is what this will come out to so that we can focus our initiatives. So if you're interested in being able to take advantage of curricular materials tailored to your needs in the future, fill out the survey. It'll definitely be worth your time and effort.
The survey mainly for academics?
So this the survey is for instructors.
Okay.
If that makes sense. So like if you're teaching a course or have taught a course, obviously that we will post the results of this, but because we're working on creating materials that would be deployable in the classroom, that is primarily the audience that we're looking for.
I see.
However, as said, that this the results of this are of more than just pure academic interest, because this will guide how to make sure that what we're doing is actually relevant to instructors.
Yeah,
and try and avoid that pitfall.
This is excellent. So now we are at 3:58, and I want to say that it pretty much happens like this all the time. We have 3 presenters, there's one more. We're just going to continue with the presentation. If people need to go, it's recorded, so you can watch it later. We're now hoping to get some questions for Josie.
So Josie, this is Chris again. Just wondering what you're going to do with the output of the survey. I mean, I think the survey is the easy part, right? It's like, who are you going to pitch it to? Who's the audience? How are you going to get sort of adoption? Because QED-C is doing somewhat of a similar analysis and inventory of curriculum and trying to assess needs as well. I think it's fantastic, by the way.
So Josie is in the same department as Heather Lewandowski.
Yeah.
Okay.
So yeah, the work that we definitely draw on the work that Heather's doing. I guess the major difference is that Heather's interested in like looking a lot at like what industry is doing. We're specifically looking at what the education landscape is doing. So it's different enough that it merits a separate work. As said, the purpose of this survey is not just because we want to gather data on this, although that's interesting. What we're really, so like there's very tangible things that can come from this, largely, you know, especially drawing back some of the research we've done on student reasoning and whatnot. All of this comes together to build a framework that allows us to create, for instance, research-based tutorials that you can use in your class that we have validated that to help students struggle with a concept that we know is difficult. This helps us make sure that this assessment that we're working on actually is relevant to courses and covers the span of material that instructors care about without including a huge amount of extraneous information. So this is the kind of stuff that we're looking for with this.
Great.
And yes, I mean, I think these efforts are definitely in conversation with each other, but they are sufficiently different that they merit these separate but related efforts. But yes, we work closely with Heather and Mike Bennett and others at our institution. One of the great things about being at CU Boulder is that we have so many people working on this from slightly different angles.
Cool. Well, it's laudable. Certainly. Thank you for sharing. It's a great presentation.
Okay. So any other questions for Josie? Well then, thank you so much for coming here today and for this presentation. I did have 2 questions that I collected from you. One matched really well with some of the surveys that we did last year and the year before. The second one, I just want to mention because we always ask, do we have any questions? Do you have any questions for our industrial partners? And so her second question was to our industrial partners. I just want this to be on the recording so that we can maybe address it at some point. She says, do you see a role for researchers or consultants in quantum education and ethics in partnering with your company? If so, what might that look like and what would you like to see? This is something that we could do in QED-C to find out what the industry thinks about this. Or to the extent that has been discussed before, we can just go deeper. So
yeah, and like there's a bunch of us, again, mentioning Heather Lewandowski and stuff, who are working on this from different angles. But there can easily be an academia industry divide where we get stuck in the ivory tower and are not actually doing things that serve the populations that we're trying to. So again, if people have ideas of like, what is something tangible that would be useful to you? And also beyond just education, even things like diversity and inclusion and other things I work on, I have connections to a bunch of people that are doing all this sort of work. And we're interested, we want to make this relevant to you all. And we want to hear from you, how we can do this. So yes, a lot of this work is very much in its infancy and its early phases. There haven't been 20 years of research on this. So we want to make sure that what we're doing right now counts.
All right, thank you very much, Josie. And with this, we go through to the last presentation for today. Christina Daniel is a PhD candidate in physics at Georgetown University. For her thesis project, she does research in quantum chemistry, many-body quantum physics, and scientific computation. She also holds a Bachelor's of Science in Aerospace Engineering from UCLA. The title of her presentation is Sparse Hamiltonian Approach to the Time Evolution of Molecules on Quantum Computers. Go right ahead, Christina.
Okay, hopefully you can see and hear me. Okay, and the screen. All right, so thanks for the introduction. Today I'm going to talk about a sparse Hamiltonian approach to the time evolution of molecules on quantum computers. This work is a product of multiple people, and those people are myself, Diksha Dwan, Dominika Zagid, Barbara Jones, and James Freericks, who is my advisor at Georgetown University. I'd like to start with a little bit of motivation, and that motivation is to use a quantum computer to do something useful. As an intern at IBM Research right now, this is my perspective of the current state of quantum computers. In particular, this is the layout of qubits on the quantum computer called IBM Kolkata. There are 27 qubits, counting the 0th qubit on the left. Another aspect of the motivation for this research is the idea of a molecule that is a hydrogen chain. This paper by the Simons collaboration shows a hydrogen chain with 4 atoms. The main takeaway from the previous slide is that it is possible to model a chain of hydrogen atoms. And for the sake of drawing a schematic, it is possible to draw a line through all 4 atoms. For my research, I have considered a hydrogen ring, which has connected ends instead of disconnected ends. You can see that there are still 4 atoms. Ordinarily and accurately, in order to analyze a 4-atom molecule, one would resort to the molecular Hamiltonian operator shown here, and there are 5 terms. 2 of them are for kinetic energy, and 3 of them are for Coulomb interactions between the protons and the electrons. Keeping in mind the goal of using a quantum computer to simulate a molecule, I and others figured that it might be easier to use the Hamiltonian operator for the Hubbard model instead of the 5-term molecular Hamiltonian operator. Here's the Hubbard model. It is traditionally applied to materials in solid state physics, but here we're going to apply it to a molecule. And the advantage of the Hubbard model is that not only does it look simpler, but the matrix itself is sparse, meaning that most of the matrix elements are 0, as you can see from this plot. The plot shows the kinetic matrix, and the plot on the right shows the interaction matrix. Adding these 2 matrices together gives the sparse Hamiltonian matrix for U equals 1 and T equals 5, where U is the interaction strength and T is the hopping parameter for nearest neighbors. A few of us wrote a paper about this idea. We used the Hubbard model and a 4-site or 4-atom molecule. The ground state of the system that we considered is shown on the bottom right. You can see that the ground state is written as a linear combination of occupation number states. Since that paper has been published, I have investigated the 6-site hydrogen ring, which is a little bit of a larger system. It is more difficult to analyze than the 4-site system because at half filling, the dimension of the Hamiltonian matrix increases exponentially with the number of atoms or sites. Here are the parameters for the system that I am considering in this presentation. I set U to 1, T to 5, V, which is the number of atoms or sites, to 6, the number of up electrons to 3, and the number of down electrons to 3. So there are 6 sites and 6 electrons, just like a neutral hydrogen molecule. Using the Hubbard model, I can find the energy eigenvalues of the system, which are shown in this plot. I can find the eigenvectors, which are shown pictorially in this plot. You can see the values range from about negative 0.3 to about 0.3. The dimension of this matrix is 400, meaning that there are 400 basis states for this 6-atom system. Another thing I can do with my code is compute a lesser Green's function, which is defined in this way. You can see that I have set T prime equal to 0, and the annihilation operator C depends on time T. The left state is the ground state with N electrons. In order to define this Green's function, I need to introduce 2 more parameters, which are I and J, or indices for sites, and I set both of them equal to 1. You will see why this is done in a minute. And since the annihilation operator depends on time, it is necessary to define time and frequency parameters. And I group those together because the time parameters are closely related to the frequency parameters. For example, the sampling frequency f sub s is equal to the inverse of the sampling period capital T. And the final time, TF, by design, depends on the number of time points, lowercase n, and the sampling period, capital T. Note that the initial time is 0, and the sampling frequency is 10, and the number of time points is 4096. Using those time parameters, here is the lesser Green's function. It is a bit difficult to see the details of this signal, so I can increase the sampling frequency from 10 to 1000 to see the details at the expense of reducing the final time. The number of time points remains the same. So why is this lesser Green's function a useful quantity to consider? Recall the definition shown here. Taking the imaginary part of both sides, we see that the imaginary part of the lesser Green's function is equal to the expectation value of the number operator for spin up electrons, assuming that T is set to 0 and that both position vector indices are the same. To figure out what this expectation value is, I can use the data shown in the lesser Green's function plot. It turns out that the expectation value is equal to 0.5. And this value agrees with the system parameters, in particular that the system and each basis state contains 3 up electrons out of a total of 6 electrons. I can also compute the so-called weights and frequencies of the lesser Green's function. So shown here is the lesser Green's function after converting it from the time domain to the frequency domain. And this is an exact expression. The weight of the greater Green's function is defined as the product of matrix elements, which are highlighted in dark green. So the weight for the lesser Green's function is in light green, and the weight for the greater Green's function is in dark green. Using a classical computer, the weights and frequencies are shown here. They are centered about 0. And there appears to be some degeneracy because for a given value of omega, it is possible to have more than one non-zero weight within a threshold in angular frequency. It's possible to post-process the data using the angular frequency threshold, and the result is shown here with gray X's. So using this post-processing technique, the data appears symmetrical. And for aesthetic reasons, I can replace the X's with lines, the resulting plot shown here. And that is the end of my presentation. Thank you for listening.
Okay, so now let's hear some questions for Christina. Did you explain how the Hamiltonian matrix for the Hubbard model was formed in the code?
Mm-hmm. So I'm going to go back to the slide that shows the Hubbard model Hamiltonian operator. So as you can see, it is a sum of a kinetic term on the left and an interaction term on the right. And both of those terms contain fermionic operators. So if I can write a function that can apply a fermionic operator to a state, then it's possible to construct a term of the Hamiltonian operator. So that's essentially what I did, was apply a fermionic operator to an occupation number state. And in that during that process, I made sure that the anti-commutation relations were met.
Thank you. So I'm looking for hands in the chat or somebody, questions in the chat. Anybody with other questions? I'm not sure, people may decide to ask a little bit later. If there are no questions, then I'm going to let Christopher Bishop make a short announcement at the end on about the office hours. But thank you so much, Christina, and also all the other presenters today. And Christopher, go ahead and Chris.
Yeah, let me unmute. Yeah, Christina, everybody, that was great. Josie, Philip, Martin, bravo. This is my commercial. We run something for the QED-C called Office Hours. You may have heard of it. I think Christina was in our last session. Excuse me. It's a monthly chance for quantum information science students to meet with mentors in the private sector or working at national labs and get a sense of how to move from academia into industry. And we have mentors from many of the companies in the QED-C, and we encourage students studying quantum related subjects to join us. The next one's going to be November 3rd. I'm going to put an email in the chat where you can sign up. It's office hours at quantumconsortium.org. It's 9 a.m. to 1 p.m. Eastern Daylight Time. They're half-hour informal conversations. We have a Zoom conference room where everybody comes into the space, and then I assign mentors and mentees breakout rooms and go off and have a conversation for 15, 20, 30 minutes, and then come back. And there's it's designed to be a forum for casual conversation about what's going on in quantum in business, if you will, just simply put, right? So send a note to that email. We also have a Slack channel. Martin, I have to be the gadfly. You said you're not sure there are jobs in quantum. As part of our office hours organization, we maintain a list of opportunities at quantum companies in a spreadsheet, a Google sheet. I just put the URL in the chat. I think I just sent it to Josie.
No, you just sent it to me.
Yeah, hang on. I'm going to send it to everybody. But there are about 70 plus companies ranging across the quantum landscape. Quantum computing for sure, but quantum networking, quantum sensors, quantum cybersecurity, everything from hardware, software services. I mean, it's a wide-ranging set of opportunities, and I would encourage any and all of you who are interested to take a look. We try to keep it updated and manage it, but there's a lot going on in quantum, and this is where I get to wax philosophic and get on my soapbox. Quantum information science is going to deliver value if we can accelerate the participation of smart people like all of you and your colleagues with all candor, the private sector, right? Helping people understand what it is and what the benefit's going to be and how we might adopt it and apply it. So that's my 2 cents. I'll put the Slack channel URL in here as well, or send me an email if you want to be added. There's the Slack channel. Connect with me on LinkedIn for sure, but here's my email address. Chris@improvisingcareers.com. And if you're interested in joining office hours November 3rd, please send me a note or join the Slack channel. We post information in there as well. So, Adrian, thank you.
Oh, you're very welcome. With this, Martin, Philip, Josie, Christina, thank you so much for coming here today. This was our last session for the year. We will see you all in 2023. Thank you once again. Bye-bye.
Hey,
Thank you very much.
So the link that you just dropped in for the Slack doesn't actually have the link that I need to register for it. It just links to the ability to go to Slack to
sign in.
Sign into Slack, but it doesn't give any information on how to sign into this particular workspace.
Okay, well, you know what? I'll use your email address and I'll send you an invite, right?
Okay, wonderful.
Probably the best way to do